Hello everyone, we will be going through our week 4 tutorials, which is on Uggkonen's algorithm. You learn it in your lecture for week 3, and we'll be going through all of your tutorial questions. But before I begin with your tutorial questions, I'm going to go through as a recap what is Uggkonen, what is a suffix tree, suffix try, and what are the 4 trees, your 3 rules or cases, and blah blah blah. Okay, your video will be separated into 2 parts. One is all the way up to what Uggkonen is with the rules, and another one is the one with all the streets. I'm going to be explaining it using one very simple example, which I believe should cover around 80-90% of what you need to know. And from there on, everything else is from you to come up with cases on your own, and you experiment with it so you really understand what is going to be happening. Uggkonen is probably your most difficult algorithm, which you will learn in your entire unit. Difficult in a way, conceptually it seems very simple, but putting it all together as you program is actually a challenge, especially if you want it to be working 100% without any issues. So let us begin. Okay, so our focus is on Uggkonen's algorithm. As I mentioned, Uggkonen's algorithm is mainly relying on the rules and the streets. More specifically, you're having 3 rules and 4 streets. My explanation, once again, is a tutorial or a lab session. It's not meant to be a lecture. I'm going to be explaining it a little bit more from a programming point of view, like how are you supposed to implement your Uggkonens. What Uggkonen does is it actually generates a suffix tree. Okay, it actually generates a suffix tree. What you have been learning or doing from 2004 is to get a suffix try and generate a suffix tree. So they are actually a very similar outcome, right? Ultimately, you have a suffix tree, but you generate it a little bit differently. And your naive construction is actually how you have been learning it in 2004. Okay. Then in the first video, we are going to discuss your slow Uggkonen, and then how when you include 4 streets, right, and suffix link, it becomes O of n, which is really fast. Then in another video, I'm going to discuss about your application of suffix tree and suffix array, right? In your exam, we usually provide you with a problem and we ask you to solve it. And then you want to explain how you can use Uggkonen to make a suffix tree to solve your problem, how to make a suffix array from a suffix tree to solve your problem, so on. And ultimately, you are going to see it as your assignment question no matter what. It's too important for it not to be in your assignment question, and because it's something which is large, you should expect it to be worth quite a lot of marks, maybe from 5% of your final marks all the way up to 10%, right? Depending on the difficulty of the question. So let us begin. Okay, before we explain about suffix tree, I want you to really understand what is a suffix. If I were to provide you with a string of A, B, C, D, E, right, what are the prefixes and what are your suffixes? Prefixes are what you go from the front, and we usually have a termination character, right? We usually call it as your terminal character to denote your at the end of the string. A very common mistake is you do not assume an empty string as a prefix or an empty string as a suffix. An empty string is actually a prefix or a suffix, right? So how are you supposed to show an empty string? You're going to have your terminal character on its own. So in your exam as well, when you're drawing a suffix tree, right, when you're listing out of the suffixes, or you're listing out a suffix array, right, you also want to include an empty string. If we go look at the suffixes, here will be the pattern which we will be observing, right? A, B, C, D, E, B, C, D, E, right? It goes from the back. It goes from the back one by one. And once again, you also want to have a terminal. The combination of prefixes and suffixes, if you realize by now, is you can use it to build substring, right? So a substring is a prefix of a suffix or a suffix of a prefix. So what you see here is actually a suffix, right? Here is a suffix. And if you were to look at the prefix of a suffix, you actually have the substring B and C. Okay? Then if I were to look at the prefix itself, right? This is a prefix. Then I look at the suffix of my prefix, right? If you just ignore the terminal, you're going to realize it is actually a what? A substring. So by definition, a substring is a prefix of a suffix or a suffix of a prefix. So if I build a suffix tree, my traversal, which is usually when you traverse a tree, it's usually a prefix traversal, right? So you have a suffix tree and you traverse it as a prefix. You realize you're actually performing a prefix of a suffix, which in other words, you're looking at a substring, right? You're actually looking at a substring. Why are we not using suffixes of a prefix? Why are we using prefixes of a suffix? So if you were to look at your prefixes, right, you're going to notice redundancy, right? My A's are redundant. My AB's are redundant. My ABC, ABC, ABC are redundant. ABCD, ABCD are redundant, right? So if I were to make a prefix tree, right, you're going to realize I'm actually having a lot of redundancy, right? Yes, I'm saving information. I'm able to compress the information to save memory, but a lot of the information which I'm saving is actually very, very redundant. Whereas if you were to look at my suffixes itself, right, and if I were to see it, you're going to realize my tree will always begin with different alphabets, right, and then only so on. Whereas if you see here, right, it's going to be A, it's going to be B, right, you're going to realize how like redundant it is. So which is why your suffixes are actually very, very useful. Okay, so how are we able to construct a suffix tree? We have learned from 2004, right? If I have a string, I will list out all of the suffixes. 1, 2, 3, 4, 5, 6. My length is 6. Therefore, I have 6 suffixes, right? What are my suffixes? It will be A, B, A, A, B, A, A, B, A, B, A, B, A, and finally my entire string, right? Which is what you're going to see here. Of course, please do not forget your terminal. So you're actually going to be having 7 suffixes, right? Your empty string also is 1. So it's n plus 1 suffixes, which is what you're going to see here. For me to generate all my suffixes, my complexity is going to be O(n) squared, right? Because I got n plus 1 number of suffixes, and then each suffix can go up to n plus 1 characters. So which is why your complexity is O(n) squared. Okay, then once we generate it in O(n) squared, we need to insert it one by one, right? A, B, A, B, A terminal. So it's going to be A, B, A, B, A terminal. I will insert one by one, then I will insert the other one, then I will traverse through and insert whenever it is a new one, which is the one here, and so on and so on. Okay, so if you were to group it in such a way, your complexity is going to be O(n) squared. You should know from 2004 by now, because it was one of your assignments, you do not want to generate all of your suffixes. right? If I want to generate all of the suffixes, I know generating n generating all of the suffixes of a string with n characters is O(n) squared. But to save each and every one of it in memory is also O(n) squared. What you want is you're going to make use of your pointers, right? So my first suffix begin from here, it ends here. So let's say it's I to j, right? So my first suffix, my suffixes is going to be cats, I all the way to j. So instead of generating all of it and saving it in a list and then going through one by one, I just want to go through every combination of I and j, right? So I begin from 1. If I want to be more specific, this will be n, right? I'm going to go every combination of I. Clear so far? Okay. So from 2004, we have learned why try is actually not ideal. If you have a try is actually wasting a lot of memory. You're going to have a lot of nodes, right? And you're going to realize this entire path here, it doesn't branch. So I'm wasting memory on all of the nodes here. Likewise, if I were to see this part here, I'm wasting memory on all of my nodes. So you want to compress it into a suffix 3, which is also what we have learned in 2004. And in 2004, we have proved the space complexity, right? A try is going to be O(n) squared worst case for space. Okay, a 3 is going to be O(n) space. If you do not remember the proof, please go back to 2004, right? There's actually a few equations and you can solve it. You're going to have lower number of nodes. When I say space, I mean the number of nodes. Okay? The issue we are having here is, yes, we are having lower number of nodes, but we are still saving all of the alphabets. And all of the alphabets are still consuming a lot of memory. So in 3155, I mean we introduced it in 2004, we are going to represent it with something known as a sub and an n, right? So for example here, ABA terminal, right? So it's over here. 1, 2, 3, 4, 5, 6, 7. You see from 4 to 7, right? This is what I'm saving here. Okay, from 4 to 7. So instead of wasting memories and save 4 characters, I can save memory by only saving 2 integers, right? Every character is 1 byte. And integer is less than 1 byte. Usually, maximum is 1 byte. Okay, so you are actually saving a lot of memory. And you're going to need to remember what I'm showing you here, because when we move on to Uggkonen's optimization, it's going to come into play a lot. Note in your 2004 notes, right, or some of the online search, online Google, you're going to see people represent it as a sub and a len. If you think about it, len equals to n minus sub plus 1. Right, so in a way, both are actually interchangeable, right? But for the ones who have already learned Uggkonen, you know what Uggkonen is, you're going to realize your n is actually very, very useful, right? Len is actually useless. Your n is where your main functionality is, or is where it's going to be the most useful one. Okay, so your Uggkonen is actually pretty impressive. Whatever I described just now is, you have a string, generate a suffix try, from suffix try you generate a suffix tree, then you represent your suffix tree with sub and n, right, for you to save memory. So if you were to look at the step, it's 1, 2, 3, which is a lot of work. And guess what? If you're doing Uggkonen, you can jump all the way straight. Right? It's actually a shortcut, and if a very efficient shortcut which also work very nicely. To make it even better, it is an online algorithm. Right? What you do here is not online. After you draw out your tree and I say, oh, I missed out an alphabet, your algorithm will not be able to add an alphabet from what you have. But Uggkonen's algorithm allow you to add a new alphabet and your tree automatically change. Okay, so this is what Uggkonen is. You can be very, very, very fast. Okay, so you see I've mentioned implicit suffix tree here. What is an implicit suffix tree and what is an explicit suffix tree? What you have learned all the while, or whatever you see here, is what we call an explicit. Right? Now explicit are all of the suffix tree which you have learned before. Implicit are even more compressed compared to explicit. Right? When it is implicit, you're not going to see a terminal at all. So if I were to use the same alphabet, right, this is your explicit, and you can actually see it very, very nicely. Okay, but because your implicit doesn't include the terminal, right, I'm going to remove all my terminals. But you realize when I remove my terminal, the edge over here is actually empty and useless. So if you were to remove it, right, you're going to come across the form here. Then after you remove it, you're going to realize I can compress everything here again. Instead of wasting memory on the intermediate node, I can just compress it, which is what you have here. Implicit suffix tree. So Uggkonen is even more impressive now if you think about it, where I can go all the way from my text, right, to an implicit suffix tree. Right? Not only you're having a suffix tree which is well compressed, you can compress it even further, right, by making it implicit. Okay, but then the problem with implicit is you're going to realize you lose a few of your information, right? You lose out the leaf. Here is a substring of A, B terminal. Here is terminal. Here is a substring of B terminal, which you can't actually find it over here. So as space efficient as an implicit tree is, it's not really usable. It is usable for some problems, but most of the problem it is not usable. So even if you have an implicit tree, you want to convert it into explicit. And the amazing thing about Uggkonen again is I can convert from implicit to explicit in O of n. So I can save memory, right, by saving everything as an implicit tree, which save a lot of memory. Then I can still compress it. I can still uncompress it into an explicit tree for use, which is really, really impressive, right? Okay, so let us have a short break first, right? Get a short break, and I'm going to start with your Uggkonen's algorithm. Everything up to now is just for you to understand all the motivation behind what a suffix tree is, why we want a suffix tree, what is explicit, what is implicit. And also, just as a note, from 2020 semester 2 onwards, the e-assessment, right, your online exam platform has been upgraded. It now supports some more functionality, so there may be a chance where you're being asked to draw out explicit tree or implicit tree. I'm not 100% sure, but there is a chance. So because there's a chance, you really need to know what is explicit tree and what is implicit tree. Okay, so have a short break. When we come back, you're going to be bearing with me quite a bit. We are going to go through the 3 rules of Uggkonen, and we are going to go through it manually and analyze the complexity. Okay, so have a short break. Okay, so let us resume. Okay, now Uggkonen, before I explain about all of the 3 rules and the 4 streets, I want to explain about phases. Because when you implement it, you're going to implement it based on phases. Your most outer loop, you're looping through the phase. For a string of n characters, right, you're going to have n number of phases, or more specifically n plus 1 if you count the first empty phase. Okay, and in every phase, your tree will grow, right? So when in every phase, your tree will mostly grow, or it may not grow if you're at rule number 3, right? But something is always happening at every phase. So first phase will be empty. You are going to move on to the new phase when you add a new character, new phase when you add character, blah blah blah, until you have the complete implicit tree. So when you add a character, you may make your tree may become bigger, or your tree may remain the same, right? So your phases is your outer loop. You're going to begin from phase 0, which is your empty phase, all the way up to n. So if we were to look at our example here, A, B, C, A, B, right? The first phase will be an empty screen, which is what you see here. My second phase will be here, only A. My third phase will be here, A, B. Fourth phase will be A, B, C. Fifth phase will be A, B, C, A. Sixth phase will be A, B, C, A, B, right? So if you notice, as our phase increases, the length which we are processing actually increases. To be more specific, when you go from the 4th phase to the 5th phase, you're adding a new alphabet. When you go from the 5th phase to the 6th phase, you're adding alphabets, right? So you're actually growing. And if you look at the loop invariant, right, at every loop or every iteration, you're performing something, which is growing a tree, right, or extending our suffix. Okay, so at the end of everything, we are going to have our implicit suffix tree, right? And when you add the 7th phase, right, or the final phase, you're going to convert from implicit to explicit. So how are we supposed to denote when we implement, right? For example, I got a sketch of size n. Okay, I'm going to now implement a loop. Loop I from 1 to n. Okay, so I will process phase I, right? So this is where my outer loop is. So first phase, second phase, third phase, fourth phase, fifth phase, sixth phase, right, and so on. So you're going to realize you're going to have up to n plus 1 because we account for the empty string as well. Or optionally, right, we can try to begin from 0, which is what you see here. So if I were to go back to the king here, right, I'm going to loop from 0 to n, right, and it's going to fall in very, very nicely, right? So at the goal of your Uggkonen, you're going to implement a loop, right? Loop from loop for I equals to 0 all the way to n, right? You're doing one phase at a time, and every phase is performing some form of computation. So at every phase, we are going to apply rules. In Uggkonen, you're going to have 3 rules. I know you have watched your lecture by Anuja or by Taylor or by whoever your lecturer is. I'm now going to simplify it with the following. Rule number 1, you're adding a new letter to the leaf, right? Leaf of the tree. Leaf means what? Doesn't have any children. Because your leaf doesn't have any children, you can always add a new character and it is still a leaf. Okay. Second rule is you performing a branch. So if this is my tree and I want to branch it, right, I'm going to, it becomes a branch, right? This is what happens when you perform a branch. Then for the third one, it already exists. What does it mean by it already exists? Rule 3 will only make sense when you're dealing with implicit. Because if you see here, right, I want you to observe here, and I want you to compare it with here. A, B, C, A, B. A, B, C, A, B. Right? But in A, B, C, A, B, B, A have already exists. Right? B, A, and then you branch. So you have already exist. So in other words, the substring of AB, which is a substring on its own, is already existing inside my H, right? But because we do not have our terminal, right? Because we remove our terminal, they won't be separated, which is why you're going to see it here. With terminal, you can see it very clearly. It's separate, right? So there's no overlapping. But because here we could not have terminal, it overlaps. And what happens when it overlaps is we are going to have rule number 3. E have already existed. Okay, so 3 rules. I'm going to modify it a little bit more, right? When you reach the when it's rule number 1, which is about a leaf, you're going to reach the end of the tree no matter what, right? Because if you were to look at a tree, right, you're going to be at the leaf. And because we are growing a tree, right? So for example, if my text is A, B, C, D, E, and I'm currently at phase number 3, so it's going to be like this: A, B, C, right? This is a leaf. B, this is a leaf, and C, B, C is a leaf, and C, this is a leaf, right? You're going to realize this is a tree. So when I go to the next phase, right, rule number 1, right, I need to traverse to the end of my tree, right? Because the leaf is already at the end of the tree, and then I'm going to add in a new alphabet, right? Which is what your rule number 1 is. Okay? This is what your rule number 1 is. Then you can only branch from somewhere in the middle, right? Because if you're at the leaf, you cannot branch because you're only adding 1 alphabet. If I add 2 alphabet, I can branch, but since I'm only adding 1 alphabet, I can't branch. So branch needs to be in the middle where there's already an existing alphabet. I'm creating a new one. And finally, the already exists, I've already explained to you earlier. Okay, so these are the 3 rules. I can give you a definition or whatever, which is boring as hell. Let us go through an example. Okay, so I'm going to link up your phases and your rules, and I want you to see it from an implementation point of view. Okay, so if I have a string here, A, B, C, A, B, X, A, B, C, Y, A, B, terminal. This string is going to be the example we will be using throughout my Uggkonen videos. Okay, why I choose such a string is because I believe it should give you 80% of what you need to know for your Uggkonen. Remaining 20%, you need to really discuss and practice it on your own. Remember, you're in your final year, you should be much more independent, right, to try stuff out. Okay, so if we were to look at 1 to n, this is the string. We are going to go from 1 to 13 because we are adding 13 alphabets. Okay, when you implement it, right, I want you to view it a little bit differently. Okay, remember, as I said earlier, I want you to view it as phases. So in the first phase, I'm only going to have A, right? Because phase 1 is phase I, right? So phase I, you're going to have string 1 all the way to I, right? So when I'm at phase number 1, means it's 1 to 1, which is only A. phase 2 will be AB, phase 3 will be ABC, phase 4 will be, and so on and so on. Okay, so this is first phase, here is second phase, here is third phase, fourth phase, fifth phase, sixth phase, seventh phase, and so on and so on. But since we are dealing with a suffix 3, we want to look at suffixes. So if my string is A, what are my possible suffix? My only possible suffix is only A. If I have a string of AB, what are my possible suffix? If it's AB, my possible suffix is either B or AB, which is what you're going to see here. Then if I were to look at ABC, which is phase number 3, what are my suffixes? C, BC, and ABC. Right? Of course, I'm going to do it here. So you're going to notice something. If I is to denote my phase, right, I can use another pointer, which is my J. So my loop is going to be I equals to 0. Let's begin from 1 all the way to n. Then I'm going to have an inner loop, which is my J, from 1 all the way to I. Right. Then I'm going to have my suffix equals to string J all the way to I. Right. This is how you're going to view it from an implementation point of view. Then here, what we are doing is we are actually processing our string from 1 all the way to I. Right. So this is the line which you're going to see here. This is the line which will generate everything here. Right. I want you to view it in such a way. So here from J to I will be ABCA. What are my suffixes? ABCA, BCA, CA, and A. Right. So I'm not going to write the entire string out. I'm just going to write my suffixes. Okay. So I denote the phases. For every phase, right, we are going to loop J from A. We are going to loop your J from 1 to I, right? And from the loop here, right, you're going to realize this is going to be O(n) square. Right, it's going to be O of n square because my outer loop goes up to n, and when I equals to n, my inner loop also loop n. That's why I have an overall complexity of O(n) square. Okay. Now you understand the loop, which is my I and my J. I'm now going to show you, right, how we build and grow a Uggkonen tree. So I'm going to keep the cable on my left. Why? Because it's going to be very, very useful for you afterwards. And on the right, it's going to be my tree. Okay. The first thing here is my root. Phase 0 is always the root, my empty string, right? So I'm going to have a root, which is what you see here. Then I'm now at phase number 1. So my pointer I is going to be at number 1. Then if you remember also, I'm going to have a pointer J, right? Because I have a loop here, I and J. So at the beginning, I will begin from 1, right? Then the inner loop, my J will also begin from 1. So my suffixes is from J to I, which is only my alphabet A. So I begin from my root. I want a suffix of A. Do I have any A? I do not have A. So I insert in a A. Note, this denote a leaf. Okay. Then I finish with my outer. I finish with my inner loop. I go back to my outer loop and increment my I. My I is now at position 2. My J is initialized back to 1, and I go from my J from 1 all the way to I. So my first suffix is AB. I begin from my root A. Because it is already a leaf, it's going to be rule number 1. I'm going to put in a B, right? That's why it is AB. Then increment my J. Now my suffixes is B. Begin from the root, right? Do I I'm looking for B. Do I have a path for B? I do not have a path for B. Because I do not have a path for B, I need to perform a branch, which is rule number 2. I branch out the B. Okay, I branch out a B. Okay, then I'm finished with my phase school. Inner loop is finished. Go back to my outer loop, increment my I becomes 3. Now inner loop, J from 1 to I. So I is 3, J is 1. So from 1 to 3, my suffix will be ABC. Begin from the root A, that's above, B as above. Do I have a C? I do not have a C. So I'm going to add in a C. Now I'm going to have above of ABC. Remember, this is actually rule number 1, right? If it's already a leaf, just add a new alphabet at the leaf, right, on the edge connecting to your leaf. So it's going to be ABC. Then increment my inner loop, my J increment now is from 2 to 3, which is BC. Begin from the root, I have a B. I do not have a C, right? BC. B, do I have a C? I do not have a C. But because it's already a leaf, it's going to be rule number 1, and I just put in the C. Okay. Then increment my J, right? Now I'm at C. Begin from the root. Do I have a J? No. Branch out for alphabet C. Okay. Then go to phase number 4. Okay. Before I go to phase number 4, I'm going to guide it up. Okay. It means rule 1, and rule 2, rule 1, 2, and 3, right? So this is for I equals to 1, J equals to 1. Here is for I equals to 2, J equals to, right? So if I were to simplify, here will be I, here will be J. Right, when I is 1, J is 1, it's going to be 2. When I is 2, J is 1, it's going to be rule number 1. When I is 2, J is 2, it will be rule number 2. When I is 3, J is 1 is rule number 1. I is 3, J is 2 is rule number 1. I is 3, J is 3 is rule number 3. Right. So I'm just keeping track of all the rules. Right. Why? Because it is from this table, you're going to understand what are my 4 streets. Okay, so when I move on to the streets of Uggkonen, your table here is going to help you understand it perfectly. Okay, so let's see what is happening. New phase, I equals to 4. Right, remember my J always begin from 1. So A, B, C, A, right, A, B, C, A, A, B, C, A, A, B, C. Oh, I've reached a leaf. What happens if you reach a leaf? Right? Because we only extend it by 1 alphabet, we know we just put 1 new alphabet, which is rule number 1. Then increment my J, right, which is B, C, A. B, C, right? B, C. I've reached a leaf. My last alphabet is going to be B and C, is going to be A. Just put a A, rule number 1, right? Then CA is going to be rule number 1. Finally A. What is my rule? If it's only A, begin from my root A, and I've reached the end. When you reach the end, means it have already exists, which is rule number 3. Okay, this is rule number 3. So tidy up. Increment my I. Right, now I go to phase number 4, and phase number 5. Repeat the same case, right? If you see here, I will be here, A, B, C, A, B, A, B, C, A. Then I reach a leaf. New alphabet, put it in. Rule number 1. Rule number 1. Rule number 1. A, B is rule number 1. A, B. F already exists. F already exists. Rule number 3. Okay. Then the next one, right, which is only B, already exists. Rule number 3. Tidy it up. So can you see the difference between rule 1, 2, and 3? Right. Rule 1 will only occur when you reach a leaf and you just put a new alphabet at the edge of the leaf. Right. Rule number 3 means it have already exists. And rule number 2 is you need to branch out. You have not reached a leaf, but you see a new alphabet. So your path has to branch out. Okay. Next one, right, is the same key. A, B, C, A, X. So A, B, C, A, B. I reach a leaf, new alphabet X, just put in a X. Rule number 1. Then increment it, right? So it's now B, C, A, B, X. So B, C, A, B, can put in a X, which is our new one, rule number 1. Rule number 1. Now, A, B, X. What is happening here? A, B, X. Do I have a path? No. Is it a leaf? No. Right? If it's already a leaf, I can just put in an alphabet. But if you see here, I still have other alphabets. Means it is not a leaf. So rule number 1 is already out. There's no such thing as rule number 1 anymore. Then it cannot be rule number 3, because for rule number 3 to exist, here needs to be X. Right? A, B, X. It needs to exist for it to be a rule number 3. So it is also already off. We are only left with rule number 2, which means we need to branch out. Right? I need to create a path for ABX. So there's a possible path of ABX. Okay? So branch it out because it's rule number 2, and here is what you're going to see. Then BX, right? B, the next alphabet is X, but here is C. It is not a leaf. You're going to realize you're doing the same thing again. Rule number 2, right? Okay, but before I move on, I want you to make an observation here. Do you notice this part is the same? CABX, CABX. So if you see here, right? CABX, CABX, right? And we branch after B, right? We branch after B. So you can actually observe similar substring. Okay? And because you can observe similar substring, right? Later on, when I introduce suffix link, you're going to understand why we can make it fast, right? Because you're going to realize you're doing the same thing. If I process here, I really need to process here, right? Then when I reach the last one, which is only X, right? Increment my J. I begin from here. Do I have a X? I do not have a X. I will branch out a X, which is rule number 2 again. Right? Once again, you're going to observe the same thing again. Right? Whenever I branch out my X, I always have something which is very similar. So you realize, right, the 3 branching are actually somewhat doing the same thing. Right? They are actually performing the same operation. Okay, then go to a new phase, right? I'm going to skip the first 3, right? Because it's going to be A, B, C, A, B, X, A, right? A, B, C, A, B, X. I reach a leaf, put in a A. Then the next one will be B, C, A, B, X. I reach a leaf, put in a A. Then repeat, right? So I'm going to shortcut it. It will be case number 1 for the following 3, right? Then A, B, X, A, right? Grab as a A, B, X, A. A, B, X, A, right? Or more specifically here, right? When J is here, A, B, X, A. A, B, X. I reach a leaf, I put in a A. That's why it's rule number 1, right? I have a B, S, A. Then increment B, S, A. You realize I have another one, rule number 1. S, A, rule number 1. Okay? Then we are going to come across the final one, which is only A. A. E, F already exists, so it will be rule number 3. Okay? Then go to a new phase, repeat the same thing again, right? You're going to realize everything else is just putting B at the back, right? Because it's going to be case 1 1 1 1 1 1 1, right? I can do it very very fast. Then we are going to go all the way to AB. What is happening here? Right? A, B. Rule number 3, because F I G exists. Go to B. I get exists. Rule number 3. I tidy it up. Then when I go to phase number 9, right? I can just instantly do a shortcut. Right? Phase number 9 will be alphabet Z, C. I can just put C all the way here. I instantly know the answer. Why? Right? Because if you look at the cable, when it's 1, it will always continue as a 1. We are just adding a new alphabet after the leaf, right? Because if you see here, if here leads you to a leaf, if A, B, C, A, B, S, A, B is already a leaf. Putting a new alphabet means I'm going to make my leaf further, my leaf longer, right? So with common sense, I can just put a new alphabet, C, 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 which allows me to be very lazy and skip everything here. Okay, which leaves me with ABC. A, B, C. Rule number 3. BC. BC. Rule number 3. C. Rule number 3. Right? Because ABC FIG exists. BC FIG exists. C FIG exists. Okay. Then go again. Once again, I'm lazy. I can just put a shortcut. Y, 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 Y. Because I can put 1, 1, 1, 1, 1, 1. Now, do you see why am I drawing my table? Right? It's for you to understand why a leaf is so important. Why rule number 1 about leaf is important. Right? And the table itself is going to help you understand rule number 1 of your Uggkonen. Right? Shortcut. Move on to here. A, B, C, Y. A, B, C, Y. I stop here. My next alphabet has to be a Y. Could I have a Y? No, I only have a X. I only have a A. So what happens if I could not have a Y? I want to create a path for Y. So I branch out. Right, which is my case number 2. Then increment my J, B, C, Y. B, C. Could I have a Y? Could not have a Y. Branch out again. Okay, but before we move on, once again I want you to observe we have the same scenario here, right? This scenario here is the same as this scenario here, right? You're going to notice very similar things. Once again, I'm just bringing it up to your attention about the similarity, because in my next video where I go through Uggkonens with the streets, you're going to understand why. Okay, then I'm going to have C, right, which is the one before, right? Then you're going to notice something again, right? I will explain of them afterwards. Last one, CY. C. My next alphabet is Y. Could I have a Y? No, I want to branch. Can you once again observe the similarity? Last one will be my Y, right? Do not have a Y, right? I do not have a Y, so I will branch out a Y, which is case number 2, right? So okay, that I will branch out a Y. Oops, where is it? Okay. Okay. Now, the next one, A. Once again, shortcut A. Right. So 1 1 1 1 1 1 1 1 1. Right. Magic. Okay, then I'm left with the last one, which is only A. Does A exist? Yes, A have already exists, right? So it will be rule number 3. Okay, so you can see why am I having the table, right? And you can see the relationship between the table and my tree. Notice, from 2 it will become 1, but once it's a 1, it's forever a 1, right? In other words, if you're forever alone now, you're going to be forever alone for the rest of your life. No. Okay, so once a leaf, always a leaf, right? When you reach 1, there will always be 1. But you can also observe, right? 1 comes from 2. Is it possible for 1 to come from 3? Right? 3 will become 2 and it will become 1. Right? You can observe here. 3, 3, 2 and finally becomes 1. Right? 3, 2 finally becomes 1. 3, 3, 3, 2 finally becomes 1. Okay? So you can actually see a number of observations. Right? And this is how Uggkonen actually function. Right? Uggkonen function by having your phase I, and at every phase you're going to look at swing from J all the way to I. Okay, so as why just now I explained about your nested loop of I and J, and then I visualize what is happening here, right? Your I and your J. Okay, so for a string of size n, I know I got n number of phases, my outer loop. Then I got every loop can have up to n surfaces, right? So this is I, this is this part is I equals to 1 all the way to n, this part is j of 1 all the way to I, right? So this combination here already gives me n squared. N number of phases, every phase can have up to n number of surfaces. Then for every surface, I need to traverse from the root, right? So if you notice earlier here, right, in my example here, right, if my surface is A, B, C, A, B, X, A, B, C, A, B, I reach a leaf. Right, I need to traverse here. So me traversing down my tree from the root all the way to my leaf will have a complexity of O of n. Right, so I'm going to have a loop I equals to 0, 1 all the way to n, loop j equals to 1 all the way to I, okay, and finally traverse. So this is O of n, this is O of n, this is O of n. So n, you're going to have O n cube, okay, which is actually worse than your naive construction. If you remember at the beginning of the video, we discussed what you did in 2004. Generate n number of surfaces, insert every surface one by one, which is O n square. Here, you'll realize you're doing it in O n cube, which is why instead of it being Uggkonen, I'm going to call it Uggkonen. Right? Not only you will be GG, but you will also feel right? This is what it is. But in the next video, I'm going to show you the 4 streets. The 4 streets is so powerful, it will be reducing it only all the way up to O of n. Right? So guess what your complexity is. If you do not know what is this meme, this is your dancing coffee meme, right? Which is popular in 2020, in case I'm using my video. Okay, so I'm going to stop the video for now and resume the 4 streets in the next video. Okay, bye.